Anna, for the introduction. Thanks to Valgrai organization for having me here today. I'm going to talk about robot swarms. And as first thing, I want to give an informal definition of what is swarm intelligence. So you can look at the swarm intelligence as a system property that is the complex global behavior that you can observe in a distributed system that is the result of local interaction between many agents. Okay? So there is no central controller, there is just self-organization. Or you can look at swarm intelligence as a research discipline that studies the collective behavior of decentralized systems, systems that are made of a population of relatively simple agents that interact with each other locally. Okay? Again, there is no global view of the environment, there is no central controller, and there is, because of this interaction, there is some resulting or emergent behavior that you can observe. So this system, this swarm intelligence system can be observed in nature and can be observed in the artificial world when we design them and we produce them. Okay? So it's important that individuals in swarm intelligence systems do not have global information, as I said, of the environment. They only interact with the neighbors. They do not exploit any hierarchical form of control or centralized form of control. This last property, at least is part of the standard classic definition of swarm intelligence. As you will see, I'm trying to go beyond. So, swarm robotics then is nothing else than swarm intelligence applied to embodied agents, to robots. So we have a large number of relatively simple robots that interact with each other, and we want them to perform tasks or to solve problems and so on. And why do we take these approaches? Because we want to have a system that are robust to failures, that are scalable, that are secure, and so on. So the problem I'm interested in since the start of my career in general, but in the last 20 years sorry, I switched to French, I don't know why, to robots, is that I want to learn how to control large number of robots so that they cooperate to perform a task that we give them, are robust to failures, are scalable, and are secure against external attacks. So there are basically two ways of approaching the problem of controlling a robot swarm, the two extremes. One is centralized control. So there is someone, a robot or an external computer, anyway, or even a human, that has knowledge about everything that happens, the status of the robots, where they are, and so on, and is in charge of controlling these robots. Okay? So in favor of this type of approach is that basically engineering is mostly about centralized control, and we have a lot of experience about how to control these systems, but we have a single point of failure, it's difficult to scale, so there are some issues. On the other side, self-organization, that is no centralized control, only local interaction, only local communication, coherent with the goals that I stated before. However, there is a problem that is an important problem that is called the micro-macro problem. So the problem is that your goal, or our goal, is to program the swarm. But in reality, we can only program the single robots. Okay? So there's this micro-macro problem that is how do you move from the specification of the swarm behavior to how to program the single individual, the single robots. So historically, what has been done is a very empirical approach to the programming of these robot swarms that consists in designing, implementing behaviors for the robots, and then cycling on experiment, testing what is the result of this design until you are satisfied with the swarm behavior, and then once you are satisfied, you start to test everything on the real robots because there are always differences between what happens in simulation, what happens with the real robot, and you recycle until you are happy. Okay? So there are starting since a few years to be more principal approaches, but for the moment I stay with this. That is the most used, most common, and it is enough for the purposes of my talk today. So how do you... What happened? I don't know. So how do you... So let me go back. So the most important step here is to design and implement the behavior for the robots. And how do you do that? Basically, again, historically, there have been three main approaches. One has been evolutionary robotics, which is a particular type of machine learning. Another one has been bio-inspired programming. That means that you look at nature to take inspiration from some similar behavior to what you want the robot to perform. And the third one is standard programming. So you give basically you give the task to a PhD students and you say, okay, find a way. And he finds a way to program the robot. So let me give an example of some work that has been done a few years ago. So we have a swarm of robots, which are called S-bots, some robots that you will see in a moment that we built for this project. They have a local sensing, and they are capable of physical cooperation. So they can attach physically to each other so that they cooperate physically. And they are controlled by stochastic rules. So the goal of the swarm of these robots that are all the same, they are all the same hardware, but they are also all programmed in the same way, is to search and retrieve an heavy object in the environment. So this is an example experimental environment where you have the robot. These are the small robots here. You have an object somewhere, and you have a goal location somewhere, and in the environment there might be obstacles. And so the goal for the robots is to find this object and transport the object to the goal location. And there are some constraints. The object is heavy, so the robots need to cooperate with each other in order to be able to move the object. The vision range of the robot is limited, so he is like here. And so they have also to cooperate to find a feasible path from the object to the goal location. Okay. So as I said before, the typical approach is to design the behaviors of the robots. So in this case, 4 behaviors were identified. Self-assembly, so the robots you see, they have grippers, so they can attach to each other. So self-assembly means that they attach to each other, they form a bigger structure. Once they attach, they have to be able to move in a coordinated way because they have tracks. So if they do not coordinate, they just get stuck. They have to be able to search for the goal, for the object, and to find a path between the two. And they have to be able to cooperatively transport the object. Okay, so I'm not going into the details, but for the self-assembly and coordinated motion behaviors, what we did was to use very simple perceptrons, basically, very simple neural networks that were evolved using an evolutionary computation algorithm. And we were able to develop the basic behaviors of self-assembly. You see here, for example, the red robots are all attached to each other, and here they are moving around together. Okay, so more interesting to explain is the bio-inspired approach for the goal search and path formation. Okay? So here the goal was, so not the goal, the idea was to somehow mimic the ants' trail formation as you can observe in ants. So you know that ants leave pheromones on the ground and then they follow the pheromone trail. However, our robots do not have pheromones. They cannot sense pheromones. So we worked by analogy, and we used robots instead of pheromones. Okay? So I will explain in a moment how this works, but let me say that the robot can distinguish 4 colors, and they can say approximately which color is closer. So the idea is the following. There are different colors, so these 4 different colors, blue, green, yellow, and red. And the robot start moving around randomly in the environment. And each robot has a certain sensing distance, okay, given by this circle. When one of these robots sees a color, and this color is at its sensing distance, so here, it has a rule that says, okay, if I say, for example, I see blue, I become, I don't remember, green, okay, and stop there. The other robots continue to move randomly around the environment. So the process can go on. For example, here this robot sees the green, becomes yellow, then the next one sees yellow, becomes blue, and so on. So virtual chains of robots can be created. So when one robot in the virtual chain, like this one, is there alone, does not see any other robot, free robot, for a while, it has a certain probability to give up and say, okay, nothing is happening, the chain is destroyed. So the net result is that you have many stochastic chains that grow in all the directions, and you can have also chains that grow from the object, for example, until one of these chains happens to find the object. Okay? Once this happens, the chain is kind of frozen, and other robots can use it to move from the object to the goal, or from the goal to object. Okay, so then we also needed the cooperative transport here, just showing that we took inspiration from another biological behavior, but it's much simpler, so I don't go into the details. Once we have these 4 behaviors, we put them together in a probabilistic finite state machine, and then, as I said before, we run experiments and we observe what happens, and if necessary, we do recycles. Okay, so what I present now is what happens after all the recycles and with a system that is working. So in the next video, in the next slide, we present a video where all the robots have the same control system, as I said before. However, when you look at the robot, you will see that they take dynamically different roles over time. There are exploring robots, robots that belong to the virtual chain, and robots that are retrieving the object. And the robots join and leave the teams all the time. Okay, so this is the experiment. So this is the object to be retrieved. It needs 3 robots to be comfortably moved. This is the goal location. These are the robots randomly placed in the environment. So once the experiment starts, you will see that chains start to happen. And they are created and destroyed. For example, I don't know, this chain here is created, and then the robot, this robot is there for a while alone, and then he gives up, and then, so the robots do not know what basically they do not know whether they belong to the chain, well, they're just applying these stochastic rules. And when one chain is created, you see the other robots are still trying to create chains, but since one of these chains leads to the object, they have another rule that says when I see something red, I grasp it, and then I start to pull. Okay? So when they are 3, they start to be able to comfortably transport the object, and they do so. And then what happens, you will see in a moment, is that these robots have a very bad vision. And at some point they make something stupid. They move away in the wrong direction. And so here, okay. And then there is another robot that is basically repairing the chain so that they can start moving back again in the right direction. Okay, so this set looks a little bit like a game and a rather simple setup. It's still the work of 30 people for 3 years. Yeah. So, what is the problem? The problem is that we still don't know how to solve this macro link in general, problem in general. So what you have just seen is basically the most complex example of RoboSwarm fully self-organized that you can find around. Also, we don't have an efficient way to interact with the swarm. As the system is distributed, you don't have a robot to whom you can talk to. Yeah? So basically, if you want the swarm to do something, you don't know who should be your reference in the swarm. And additionally, okay, when we talk of swarms, often we say, okay, since there are many robots, they are fault tolerant by design. Okay, one robot breaks down, and then the system continues to work. In reality, what happens is that broken robot can get in the way of working robot. Or if the robot is misbehaving because either it's malfunctioning or because it has been hacked, is acting maliciously, then it can disrupt the swarm behavior. We have run experiments in which we show that it is enough to have one robot that is misbehaving, and it can change completely the behavior of the whole swarm. Okay? So these are open problems. And currently, my main research direction in the last 10 years has been to try to solve these open problems, or to address these open problems, taking one particular approach that is trying to introduce some elements of centralization in a RoboSwarm without losing the nice properties of self-organized systems. So the way I approach the problem, so there are two ways in which I approach the problem. One is the one that I will be talking today. Okay, so I talk in a moment. And then the other one is by using smart contracts and blockchain technology. Yeah. Because the blockchain, as you know, is a distributed database that is can be in common between all the nodes of a network, of a distributed network. RoboSwarm is a distributed network, so the blockchain technology can be married, at least when you first see it, it seems reasonable to put the two things together. And so we recently demonstrated that this is possible and that you get all the nice properties of a blockchain in the RoboSwarm, not for free, but for a reasonable cost. Okay, so, but as I say, today I'm going to focus on this self-organizing nervous system for RoboSwarms. So, what is a robot nervous system? So basically, when you look at one robot, the robot nervous system is nothing else than its CPU and the signaling architecture that connects sensor actuators to the CPU. So we call the CPU also the brain. And then when you have two robots that have this kind of middleware, that is this self-organized nervous system, what we can do is the following. We let the two robots physically attach to each other, and in the moment that one robot attached to the other, it cedes control to the other one. Okay? It's like I was giving a hand to you, and then you were taking control over my brain. Okay? So my brain is still there. It can still control my local sensor actuators, okay? But at some level, you are controlling me. Okay, so you can extend this to many robots. And for example, here we have a situation in which there are 6 robots there is one brain. The brain has knowledge about all the robots that are attached. At the structure that you see here is a tree, and every node of the tree has knowledge about the remaining part of the tree. So when you have two of these Sans-enabled robots, like here we have this one with a brain and this one with a brain, if they connect to each other, so let's say that this robot attaches to this one, this robot cedes control to this one, which was already controlled by this one, so it transmits all the information, and this brain here immediately has knowledge about all the body. Okay. So this is interesting for a number of reasons. First, you can start to have a robot. Let me stop a second while I restart. You can have systems where you start with, I go back if it's possible. Yeah, you start with many robots, each of which of them is a brain. Okay? And then here I'm considering a stimulus perceiving and pointing behavior. Okay? So when a robot sees this green light, it switches on its LED in the direction of the stimulus. If the stimulus is too close, it backs away. Then I let the robot form two bigger structures, each with one brain. And then I let the stimulus appear again. And now you will see that this robot can act as single bodies. So only the closest part of the body is switching on the green light. And again, here, they attach to each other, and when the green light arrives, only one robot, the closest one to the light, switches on. Okay? This would be extremely difficult to do if each robot was independent of the other. Also, when the light is approaching, the whole structures move away. Okay, so we can move from a swarm of independent, autonomous robots to a single structure that acts as a single robot, and then if I let the robot here dismantle, detach from each other, they return to be a swarm of independent robots. So one thing that you get is, for example, self-healing. So here these robots are attached in this configuration, this shape, and then we induce a failure in the brain. So all the robots are attached to the brain, realize the brain is broken, they move away and they reattach, because each of them knows what is the goal, that is to form this particular shape in a kind of triangle, right? If there was a spare robot, it could have been used to reform the exact same shape as before. As it happens here, for example, here this robot here breaks down. So this robot realizes that it's broken, lets the other go. In this case, there are some free robots, spare robots, that can join and reform the same shape. You can also do in a heterogeneous world where a robot can have different capabilities. You could imagine, for example, that you have an explorer robot that go around searching for an object, and when one of them finds an object, he can ask for help to another robot that has specific capabilities for transporting this object. Okay, so as it's demonstrated here, this robot has found a brick, but he cannot transport it, so he's asking for help. So this becomes a brain of a robot with two units, where one is specialized for transporting bricks. Okay, so I don't remember how much time I have. 15 minutes more, okay. So what we have been doing recently is to extend these ideas to a heterogeneous swarm of robots, where you have both ground robots and drones. that cooperate. So we have the flying robots that can see the ground robots, and they can compute the relative position of the ground robots and the orientation. But the ground robot cannot see the flying robots. They can just Wi-Fi communicate with them, and they can avoid each other and the obstacles. So these are the simple communication capabilities and sensing capability of this heterogeneous world. So the idea is the same as before. We have any of the robots at the beginning, they are not attached to each other. Okay, I will explain in a moment. But any of the robots can be the brain, and they can form structure. For example, here, this drone is the brain, and the structure is these 2 drones and 4 ground robots logically attached to each other. And here there is another one, another zones, where there is only 1 drone and 2 ground robots. And again, as previously, when they meet, which means that one robot of one structure sees a robot of the other, they can join and become a single zones. Okay, so let me give an example. So here we have, again, flying robots and ground robots. The flying robots are the red dots, and the gray one are the ground robots. As I said, all the robots have the same information. And the goal for the swarm is to organize into this shape. So this is the shape, and this is the logical structure of the hierarchy that is going to be created. So the way this works is the following. As I said, each robot starts in the brain status, and then when a flying robot sees a ground robot, it tries to recruit it. If it is free, the robot accepts. So in this moment, these 2 ground robots are recruited by Fi. Then, if another robot arrives, like this drone, Fk, and which has previously recruited this ground robot, if it sees this robot here, this ground robot, it tries to recruit it. And then there is a number of messages that are exchanged in which the drone tries to recruit it, the other one, the ground robot says, no, I cannot because I'm already recruited, and it tells this drone to ask to its owner, and then there is an exchange of messages, and the result is that this drone is recruited into the partial zones that is being built. So obviously, all this happens if adding this drone is coherent with the goal of the brain, that is to form a particular shape. Okay, so the process goes on and is repeated with these simple rules until you get the final shape. At this point, if there was another drone or another robot, it would not be considered because it is not missing in the shape that is the goal for the swarm. Okay, so all this process can go on in parallel, and if you are in a finite arena, so that the robots have to meet each other sooner or later, it will end up in the desired final structure. Okay? Every time the 2 substructures meet, they join, and once they are all joined, they rearrange. So the interesting thing is that once you have this kind of middleware, you just give the topology, and you don't have to program anymore. So everything happens kind of automatically. So we have started to run experiments with the real robots. By the way, making experiments with the drones is a huge amount of work. And it's working. Yeah. Okay. So here, what you see here, all the robots, they are placed one after the other. The goal, the target shape is this one, and the drones and the ground robots are adapting to each other position until they manage to create the desired shape. Okay, so this is the desired shape. You see this robot is not here just because it's from the top. Okay, so okay, this is very short. It's same example as before. Also, in this case, we can recover from failures. So in this case, you put a new robot, it adapts immediately to the shape, and no problem. And okay, so here is an example in which we show that exactly because each robot is independent, is an autonomous agent. If you, for example, put obstacles in the environment, the ground robots try to avoid the obstacles. And the drones are moving towards this final goal location. So the whole structure, you see the shape is a bit lost while the ground robots are avoiding the obstacles. But again, you don't need any particular reprogramming. They're just adapting, reacting locally to what happens. And as soon as the low-level disturbances are no longer there, they retake the shape that they had at the beginning. Okay, so they can also be programmed to do decision making. Here is an example where the robots first start with this shape, then go through some obstacles, and then they have to reach this object to encircle it. And there are two passages, and the swarm can identify which of the two passages is bigger, and then change shape to pass through the passage. Okay, so you can one thing that you can do is you can give many different shapes as a library of possible shapes to the robots, and then they can select the one that is most appropriate. Okay, so there is still some programming, obviously, but it's like it's a way for programming the swarm without. Yeah, I'm done. Without programming every single robot. It's not always working, this. Yeah, yes. Okay, so in this one, we have some adaptation. So the goal for the swarm that is here is to reach this object while taking the shape as before. However, when the shape that is these 6 ground robots in this position approaches these obstacles, they try to shrink, but then they can no longer shrink enough, and they decide to change completely shape, and then to change shape again when they have reached the goal. Okay, so all these experiments have shown up with real robots, so we have a limited number of robots, and especially is a limited dimension of the experimental arena. But we have shown in simulation that you can work with, for the moment, up to 250. And the reason we didn't do more is because our computer does not, our computers do not support, not even Amazon computers support more than 250 at the moment. But you see, they are given this usual kind of formation of in 3 layers. And when we look at what happens when we increase the number of robots, we see that some interesting results. So here, what is shown here is the number of robots in the swarm from 5 to 225. And this is the error per robot. Okay. And the error per robot tends to increase, but not that much. And the reason why it increases is because the robots are logically attached to each other. So when there is 20 robots, the last robots in the structure have probably some error. So the next one that attaches has also some error with respect to the previous one, plus the error induced by the previous one. On the other side, when you look at the communication, the amount of communication, you see that it tends to stabilize. So which means that when you grow, at some point, there is no more communication per robot. Each robot uses the same amount of communication to reach the final configuration. And similar for the computational effort of the robots. It tends to stay constant, while the convergence time increases, and this is kind of obvious because you have to grow. Okay, so yeah, we made also some other scalability experiment in which we were running with, I don't remember how many robots here, but maybe 100 or something. One of these decision experiments where we show that the swarm is capable of converging to very good shape. Then in the moment in which it has to pass through these passages here, the error increases a lot, then it goes down again, and then when it's given the command to create this final shape around the object that represents the final destination, again, there is an increase in error because the swarm is rearranging, but is then converging again. Okay. So it shows that scalability works and continues to work when there are changes in the shapes during the performance of a particular task. Okay, so to conclude, this SONS approach allowed to switch between these purely self-organized organization of a swarm that is typical to swarms that have some kind of a hierarchical, some kind of centralized control. Okay. So the advantages are that now we have a brain. In some occasion, so imagine that you have this swarm and then you want to cover some space for surveillance. Then in that case, probably the best way to do so is in a self-organized way. So you let the robots go around, they move randomly, they distribute. And then at some point, something dangerous is identified. And then they can create this hierarchically self-organized structure that encircle the object that is dangerous. Okay? And once this is done, there is one of the robots in this new structure that is the brain. So if you want to tell the swarm what to do, you have a specific robot with which you can interact. And also, okay, it can do this, but at the same time, it retains properties that are typical of a self-organized system that are desirable, like robustness to failure, rapid adaptation to local contingencies, because each robot remains an autonomous independent robot with a local computational capability. So not all the computation is given to the brain. Okay? Each robot has its own computation. So, for example, imagine that one of the ground robots that are far away from the brain has some sensing capabilities. It can use its own computational power or capacities to aggregate this information that it senses, and it can pass only some compressed information up to the brain. And okay, and then we have demonstrated scalability. Okay, so these are the people that are working with me on this project, 3 postdocs and 3 PhD students. Basically, US, Australia, Africa, Asia, and Asia. So we cover, with me that I'm European, we cover all the continents. Okay, thank you for listening. So if there are any questions. So one fascinating question about the swarm of students is why they always sit in the back of the large rooms.
Thanks for the presentation. I found it quite interesting. I do have a question, since I'm not in this field. I'm kind of curious of the practical usages of these types of systems.
Oh, sorry, I didn't get the practical success.
Yes.
Yeah, it's, I would say that is basic research. Is I'm not aware of real-world applications unless some military are using it. Yeah. One of the limitations, I think, is given by the capabilities of the robots. So in the sense that we have all autonomous robots here, and as you know, there are not many autonomous robots in our daily life, right? Because, not because there are not possible applications, but because the robots are not good enough or economically ready to be used in the real life. And here we are working on many of them cooperating. So until we have some application where as I say, the military for sure is one possible application, because you can imagine a swarm of these drones, and the fact that you can kill some of them and the shape is self-organized is a possible application. But I'm not working with military, so I don't know.
I just was curious, since this is not something I'm not researching actively in this area, so I was just curious, yeah.
When we have seen the dots moving and shaping in the way that they are structured in a kind of, is that their decision because of they have to organize at
this one, sorry, the next one.
Yeah.
This one.
They organize that why? Because of what kind of instructions they have to, or they can do whatever they want, or there is something that they have to.
Now, in this case, in this particular case, since the goal is to study scalability, we give the robot one particular shape, and they have to form it.
Okay. But depending on the context, they can decide what is the best shape to adapt, or.
Okay, so in other situation, like for example, in this experiment, they are given some shapes, and they select which one. So the brain selects when it arrives here. When they arrive here, the brain sees this passage and they select the shape that is appropriate.
Any moment, no? They don't decide from the beginning because
No.
they are taking the decisions in the context they are approaching, yeah?
Yeah,
Ah,
yeah.
Okay, nice.
Yeah, at the beginning they just have the goal of creating this shape, and then they have the option to select another one, and this is triggered by the sensing. Yeah, there's.
So we see these incredible demonstrations of robots like this giant dragon, I think I saw on social media in China just a couple of nights ago. How are those programmed to make these giant animated shapes in the sky? And is this technology, is it related to this technology? And I guess a related question is the local communication, how much could that be relaxed? I mean, how does it relate to traditional distributed system design, I guess?
Okay, so what you see, I guess you refer to these nice dragons. Yeah. So these are completely fully central control, and is absolutely not robust, and it takes an enormous amount of work to make it work once.
So do they have a global radio network somehow?
I don't know the details, but they have a way to, well, they probably use a military-grade GPS.
Okay.
Yeah, okay. I can repeat the question if you want.
I was thinking if there was the possibility of, instead of having physical swarm robots, you could have kind of virtual ones that were working instead of a physical environment, for instance, in a network, in a virtual network, and applying the same kind of algorithms to communicate between them so they can move around the infrastructure, for instance, looking for, let's say, vulnerabilities or whatever.
Yeah.
If there has been some development in this area.
So since, let's say that in the last 15, 20 years that I've been focusing on real robots, I didn't follow too much that direction. But when, some 20 years ago, I was working much more on the software agents. We developed, for example, algorithms that go around the net to collect information to provide adaptive routing, for example. Okay? So basically, yes, you can.
But I don't mean individual robots, but swarm robots using this kind of thing. Okay.
Yeah, a swarm of these robots that they move on the net. They act. In some moments, they act like data packages, so that they experience the same type of delay or issues that standard data packages. And then they use the information they collect to change the way the information is distributed over the net. Yeah.
Thank you.
So we have done experiments on simulated networks, but this is not the way that the real net, the internet works, because there are other priorities. The stability, for example, is much more important than the efficiency. And our system is very efficient, but it's much more difficult to guarantee stability. Okay.